Hi everyone, welcome to goclasses. So in the last lecture, we were discussing functional dependency. This concept we have already seen. What is the concept of functional dependency? What is the definition of functional dependency? Okay. So this concept we have already seen. Now let's solve this question. Tell me the answer for this question. Is this functional dependency AB determining C, is it same as BA determining C? These two functional dependency are the same. Tell me, these two functional dependency are the same? The answer is yes. What is the reason? Tell me what is the reason? The answer is yes. Because I told you that this AB, this is actually just a convenient notation for set AB. This is your set containing AB. Yes or no? Is this clear? I told you that this is just a simple notation for set containing AB. This is just a simple notation. Okay, this is just a simple notation for set containing AB. Okay, and set is unordered collection. Yes or no? You already know that in a set, order does not matter. This set A comma B, this set is same as B comma A. These two sets are same. In a set, order does not matter. Okay, because these are basically set. Okay, so very simple point. Remember this, that this is just a convenient notation. This is just a simple notation for set containing AB. Okay, so remember, when you say that AB determining C, then basically what you are saying, basically you are saying that this set of attributes, this set of attribute determines, this set of attribute determines this set of attributes. Is this clear? Let me know. Okay, so this set determines this set. Very simple point. Okay, and convenient, for convenience, okay, for simplicity, what we do, just for simplicity, what we do, we write it that AB determines C. This is how we write for simplicity. This is just for simplicity, nothing else. I told you. Okay, now tell me the answer for this question. Given an instance, can we find out what are the functional dependencies that are defined over schema? Tell me, given an instance, can we find out what are the functional dependencies that are defined over the schema? The answer is no. The answer is no. See, from an instance, you can eliminate some functional dependency, but you cannot say that some functional dependency are they will hold on the schema. Yes or no? So from instance, what we can do? From instance, if I give you some instance, then from that instance, we can eliminate some functional dependencies. We might eliminate some functional dependencies. Yes or no? Some functional dependencies we can eliminate, but we can never say that some functional dependency hold on the schema. But we can never say that a functional dependency holds on the schema. Okay, is this clear? So we can never say that some functional dependency holds on schema. I hope this point is clear. Okay, so this also we have already seen. I told you this, you can read this. Okay, so you can easily see that by looking at an instance, what we can do, if I give you some instance, then what we can do, we might be able to eliminate some functional dependency. We might be able to say that some functional dependency does not hold. Okay, but we can never deduce that a functional dependency will hold. Okay, if you are saying that a functional dependency holds on the schema, then what should happen? If you are saying that a functional dependency holds on the schema, then what it means? It means that all the legal instances will satisfy. All the legal instances should satisfy that functional dependency. Okay, so this we have already seen. Now let's move on. Now you can see, so functional dependencies that are defined over the schema, they will be given in the question. Yes or no? From the instance, we cannot find out the functional dependencies. Do you agree? If I give you some instance, from the instance, you cannot find out functional dependencies. Okay, so functional dependencies which are defined over the schema, these will be given in the question. This information will be given in the question. Okay, now let's move on. Tell me the answer for this question. Given an instance, when can we say that it is legal instance? If I give you some instance, then when can we say that it is a legal instance? If I give you some instance, then when can I say that it is a legal instance? Legal instance simply means that it satisfies all the integrity constants. Okay. So this is the definition of legal instance. Legal instance simply means this satisfies all the constants that we have put. This satisfies all the integrity constants that we have put. All the integrity constants that we have put on the schema, that we have defined on the schema. Is this clear? Defined over schema. So remember, when you say legal instance, or I can say valid instance, either you can say legal instance or you can say valid instance. What this means? This means an instance which satisfies all the integrity constants that we have put on the schema. Is this clear? Okay. Tell me. So all the integrity constants that you have defined on the schema, they must be satisfied. This IC, what this means? This means integrity constant. Okay. All the restrictions that you have defined on the schema, those restrictions must be satisfied. Then you can call it valid instance. So these are the definitions. So we have seen everything. We have seen what is the definition of functional dependency. When can we say a functional dependency is satisfied by the instance? That also we have seen. If I give you some instance, then that instance, when that instance will satisfy functional dependency, that we have seen. Now, remember, schema will satisfy functional dependency if every valid instance will satisfy functional dependency. So these concepts we have already seen. Okay, so you can just check it out. In the previous lecture, we have already seen all these concepts and many questions we have done. Okay, now let's see the next concept, that is functional dependency laws. Some rules we need to study. Okay, what are theorems? I can say theorems or rules for functional dependencies. So these are some theorems that we need to see. We need to see what are the rules associated with functional dependency. So let's start one by one. Let's see the first rule, that is reflexivity. This rule is basically the law of trivial functional dependency. Okay, what this says, this reflexivity law, what this says, this reflexivity. Okay, this is the reflexivity law. What this says that if X is a subset of Y, or I can say if X is a superset of Y, tell me, if X is superset of Y, then what will happen? If X is superset of Y, then can I say that X will determine Y? Tell me. If X is a superset of Y, then can I say X will determine Y? Yes. This is your definition of trivial functional dependency. Yes or no? Okay. This is the definition of trivial functional dependency. You already know. So remember this reflexivity law. This is basically the law. This is the law of trivial functional dependency. This is the law of trivial FD. Okay. Very simple point. So this is your first law. Okay. Reflexivity. This means law of trivial functional dependency. If Y is subset of X, then I can say X determines Y. This type of functional dependency is called trivial functional dependency. Okay. Now let's see the next rule. The next rule is augmentation. What is this rule? This rule says that if X determines Y, then XZ will determine YZ. Okay. This is the augmentation law. What this says? This says if X determines Y, then XZ will determine YZ. Can you prove it? Tell me, can you prove it? Can you prove it? See, before proving it, let me tell you something. Remember, when can you say that a functional dependency does not hold? Tell me, what is the violation of a functional dependency? Violation of a functional dependency. Tell me, when can you say that a functional dependency is violates? What is the violation of functional dependency? When violation will happen? Violation of functional dependency, what should happen? This type of situation you should create. If you want to say that violation of functional dependency happens, okay, then you should create this type of situation. What you should do? You must create this type of situation that you are putting some value X here, okay, in these two tuples. In this tuple, you are putting value X. So in these two tuples have same value. For alpha, these two tuples have same value, but they have different value for beta. They have different value for beta. Okay. So remember this. If you can create this type of situation, then we will say that alpha does not imply beta. Is this clear? So remember, this is the violation of alpha implies beta. I can say this is the violation. This is the violation of alpha implies beta functional dependency. Okay. If you can create this type of situation, if you can create this type of situation where Y is not equal to Z, okay, If you can create this type of situation, then what it will mean? Then what it will mean? Then it will mean that this functional dependency is not correct. Yes or no? Okay, so remember, if you can create this type of situation, this will mean that alpha does not imply beta. Or I can say alpha implies beta is false. Yes or no? I can say alpha implies beta is false. Is this clear? Let me know. So very simple point. Now tell me, if you can never create this violation, then what it will mean? If you can never create this violation, if we can never create such violation, if we can never create such violation, then never create such violation. If you can never create such violation for alpha implies beta functional dependency, then tell me, then it means this functional dependency holds. Yes or no? Then this functional dependency holds. Is this clear? Let me know. Okay, very simple point. So remember, if you can never create this violation, you can never create such violation, then it means that this functional dependency holds. Okay, is this clear? So very simple point. Now, what we need to prove? This is your augmentation law. This says that if x determines y, then xz will determine yz. Okay, so this is your augmentation law. Can you prove it? So let's prove the augmentation law. First of all, you tell me what we need to prove. First of all, you tell me what we need to prove. Let me know. What we need to prove? We need to prove that xz determines yz. This is what we need to prove. And what is given? And what is given? It is given that x determines y. Yes or no? So x determines y. This is given. And we need to prove that xz determines yz. Okay. So let's try to create a violation for this. If we can create violation, then this statement will be false. If I can never create a violation, then this statement will be true. Yes or no? Is this clear? So remember, this is already given to you. This is already given to you. X determines y. This is given to you. And what we need to prove? What we need to prove? We need to prove that xz determines yz. So we can prove it by contradiction. Okay, what we can do? We can prove it by contradiction. We can prove it by contradiction. How to prove it by contradiction? Let me prove it by contradiction. What I will try to do? I will assume that this functional dependency does not hold. Okay, just assume for a moment. Just assume this functional dependency you can violate. Okay, assume that this functional dependency does not hold. Okay, is this clear? Just for a moment, assume that this functional dependency does not hold. Okay, is not true. Now tell me, if this does not hold, what that means? What that means? That means violation exists. Yes or no? That means violation of this functional dependency exists. Agree? Violation of this functional dependency exists. You can create a violation. Now, let's create a violation. Let's try to create a violation. So you have xz, you have xz, y. Okay, these are the three things you have. Now let's try to create a violation. Okay, I'm creating a violation. So tell me, if I'm creating a violation, how many tuples I need to create a violation? How many tuples I need? Tell me. How many tuples I need if I want to create a violation? I need 2 tuples I need. Yes or no? If I want to create a violation, I need 2 tuples. So let me take these 2 tuples. In these 2 tuples, to create a violation of this, what I need? What I will do? I want to create a violation of this. Then what I will do? In these 2 tuples, this I will keep same. I will keep it same. Yes or no? I will keep it same. What I will do? I will do something like, for example, AB, AB. I will keep this combination same. Okay, and then what I will try to do? Then I will try to do this combination different. Yes or no? Okay, is this clear? So in these 2 tuples, I will keep this combination same. Now, is it possible I can put different combination for YZ? For YZ, can I put different combination? For example, you can see already Z is BB. Okay, for Y, let me put, for example, C here, D here. Now, where is the problem? Okay, so can I say I created violation? Can I say I have created violation? Tell me. Can I say I have created violation? No, because remember, there is a problem here. What is the problem? There is a contradiction here. There is a contradiction here. What is the contradiction? There is a contradiction because remember, already it is given that X determines Y. Contradiction because already it is given because X determines Y is given. Yes or no? Now tell me, x determines y is given. But here can I say x determines y? Tell me. Here can I say x determines y? No. Yes or no? Agree with me? So contradiction, we got a contradiction. Okay, if you try to create a violation, then you will get a contradiction. It means what? Tell me. So remember, if we try to create violation, remember, if we try to create violation of this, if we try to create violation of xz determining yz, then we get a contradiction. Yes or no? Then we get a contradiction. Is this clear? We get a contradiction. So what that means? So we cannot create violation. Yes or no? So we can never create violation. And if you can never create violation, what that means? So we can never create violation of, tell me, we can never create violation of xz to yz. What that means? Which means this functional dependency holds. Yes or no? Which means this functional dependency holds. Please tell me, did you understand? See, very simple point. This is given to you, x determines y, and we need to prove that xz will determine yz. So what I will do, I will prove by contradiction. For a moment, assume this does not hold. For a moment, assume this is not correct. Okay, assume this does not hold. If this does not hold, then violation you can create. If this does not hold, then you can create a violation. But if you create a violation, then contradiction will happen. If you create this type of violation, look at this. If you create this type of violation, then contradiction will happen. Because x determines y. If you create a violation, then here you can notice x does not determine y. So contradiction will happen. This is what I'm saying. If you try to create a violation, then contradiction will happen. So that is the reason I can say you can never create a violation. If you can never create a violation, so this functional dependency will hold. So this is the proof. Is this clear? Please tell me. Let me know. Is this clear? Please tell me. So this is your proof. Now let me tell you another proof. Let me tell you proof number 2. This is direct proof. Okay, this is direct proof. See, these are very intuitive proof. You can take your copy pen. All these proofs are very intuitive, very simple proof. Okay, in the exam, if they give you any new rule, in the exam, they can give you some new rule, they can give you. Okay, then if you know how to prove, then you can easily solve it. Okay, so let's take a copy pen and let's do it. So this is the direct proof. What is the direct proof? Remember, this is given to you. This is given to you that x determines y. And what we need to prove? We need to prove that xz determines yz. This is what we need to prove. Now, if you need to prove this, then what you need to do? Tell me. I need to prove this. So to prove this, what I will do? Tell me. To prove, if you want to prove xz determines yz, then what we can do? Okay. What we can do? We can show that. If two tuples have same xz value, if two tuples have same xz value, then they will definitely have same yz value. Have same xz value, then they definitely have what they have. Then they definitely have same yz value. Okay, same yz value. Is this clear? So this is what we need to show. Do you agree with me? Do you agree with me that this is what we need to show? See, you want to prove this. This is what you want to prove. Now, if you want to prove this, then what you need to show? You need to show that if two tuples have same xz value, then they will have same yz value. Agree? This is the definition of functional dependency. So if you want to prove xz determines yz, then what you need to do? You need to show that if two tuples have same xz value, then they will have same yz value. Now let me take same xz value. Let me take some same xz value. This is your xzy. Okay. So let me take same xz value in two tuples. I am taking same xz value. Okay, means here this combination and this combination, I will take them same. So let me put A here, B here. Let me put A here, B here. Okay. Now tell me. Now can you prove that this yz combination also will be same? For these two tuples, can you say yz combination also will be same? Can you guarantee? Can you guarantee yz combination also will be same? Yes, Because remember, it is already given that x determines y. Yes or no? It is already given that x determines y. So if x determines y, now you tell me, if you have same x value in two tuples, then y will have same value in these two tuples. Yes or no? Agree? See, this is already given that x determines y. This is already given to you that x determines y. So if two tuples have same x value, then they will have same y value. Okay, that's it. Hence proved. So what we have done? So we have proved that in these two tuples, xz, this xz combination has the same value, and you can notice yz combination also has the same value. Yes or no? Is this clear? Please tell me. Okay, so this is your hence proved. Did you understand? Let me know. Please tell me, did you understand? So which proof did you like? Two proof we have seen. Which proof did you like more? Let me know. Which proof did you like more? So let me know. Did you understand both of them? See, whichever proof you like, proof number 1, proof number 2, whichever proof you like, but did you understand both of them? Both of them, did you understand? Yes or no? And can you notice in both the proof, we are using the definition of functional dependency. We are not doing something fancy. Yes or no? We are not doing anything fancy. We are just simply using the definition of functional dependency. Just apply the definition of functional dependency, nothing else. Don't do anything fancy. Just apply the definition of functional dependency. Okay, is this clear? So very simple. So this is your direct proof. We have seen the direct proof. I hope you understood. So remember this augmentation law. This is augmentation law. Okay, so this is called augmentation law. What is augmentation law? So remember, this is your augmentation law. This is important. That what this says that if x determines y, then what will happen? Tell me. If x determines y, then xz will determine yz. Is this clear? If x determines y, then xz will determine yz. Very simple point. Okay, quite simple point. It's like this. See, just notice. If x can beat y, then xz can beat yz. Yes or no? If x can beat y, then xz can beat yz, something like that. Okay, but anyway, this is the augmentation law. So we have seen the proof. You can easily prove it. We have seen the direct proof. We have seen the proof by contradiction. Any proof you can apply. That is your choice. Okay, but understand the proof. Both the proof you understand. Now let's move on. Now let's see the next law, that is transitivity law. What this transitivity says? This says that if x determines y and y determines z, then x will determine z. Okay, this transitivity, this says that if x determines y, y determines z, then x will determine z. X will determine z. This is the transitivity rule. Okay, this is the rule of transitivity. This says that if a1 to an determines b1 to bm and b1 to bm it determines c1 to ck, then this will determine this. Okay, so this is the transitivity law. Is this clear? So quite simple. Okay, so remember what this transitivity law says. First you understand this. What this transitivity law says. This says that, it says that, for example, if AB determines C, and let's assume C determines DE, then what will happen? Tell me. If AB determines C, okay, this AB determines C. Remember, this AB can determine C, and this C can determine DE. This C can determine D. Then this transitivity, this says that, now this says that AB determines D. Okay, so this transitivity, what it says? It says that AB determines DE. This is the rule of transitivity. Okay, again, can you prove it? Again, can you prove it? Tell me. Can you prove this law of transitivity? Let's prove it. So let's prove it. So tell me how to prove it. You can prove it by contradiction, or you can apply the direct proof. Let's apply the direct proof. Okay, let's apply the direct proof. If x determines y and y determines z, then what we need to prove? Then prove that x determines z. Is this clear? This is what we need to prove. So tell me, what is given and what we need to prove? This is your statement. Now tell me what is given. What is given? Here what is given? It is given that x determines y. Also it is given that y determines z. This is given. And what we need to prove? What we need to prove? Tell me. What we need to prove? We need to prove that X determines Z. Okay. Now apply the direct proof. Apply the direct proof. In the direct proof, what I will do? Tell me. In the direct proof, what I will do? Let me know. If I apply the direct proof, then what I will do? This is what I need to prove. So what I will do? I will show that if T1, if two tuples have same X value, then they have same Z value. Yes or no? If two tuples have same X value, if two tuples have same X value, then they will have same Z value. Yes or no? Then they will have same Z value. Is this clear? This is what I need to show. Do you agree with me? I need to show. This is what I need to show. I need to show that if two tuples have same X value, then they will definitely have same Z value. Can you prove it? Can you take a copy pen and can you prove it? Can you try? Can you try? Let me know. See, very simple. We need to prove that this is your X, this is your Y, this is your Z. Okay. We need to prove that if two tuples have same X value, then they will have same Z value. Okay. Two tuples, you take two tuples, T1 tuple, T2 tuple. In these two tuples, you take same X value. Same X value you take. Now we need to prove that this value and this value must be same. Okay. Yes or no? Now we need to prove, show that these must be same. Okay. We need to prove, remember, we need to show that these will be same. These will be same. Is this clear? These will definitely be same. This is what we need to prove. So tell me how to do that. How to do that? Very simple. It is already given to you that X determines Y. It is already given to you that X determines Y. So because X determines Y, so what should be these two? These two values, they must be same. Yes or no? X determines Y. So if two tuples have same X value, they must have same Y value. Okay. Is this clear? So from this, what I can say, because of this, X determines Y. Because of this, what I can say that in these two tuples, Y value will be same. Yes or no? Y value will be same. Is this clear? Please tell me. So because of this, I can say this will happen. Simple point. Because of this, this will happen. Okay. And also it is given that Y determines Z. It is also given that Y determines Z. Okay. It is also given. What is given? That Y determines Z. Now tell me. Y determines Z. Now tell me. What this means? This means that if two tuples have same Y value, they will have same Z value. Now you can notice these two tuples, they have same Y value. So they will have same Z value. Yes or no? Yes or no? So these value will be same. Is this clear? So these two values, these will be same. So please tell me, did you understand? Let me know. Is this proof clear to everyone? So you can notice we started here. Please notice we started here, and where we got here. So it means X determines Z. Is this clear? Please tell me. So what it means? So it means that X determines Z. Okay. So what we have proved that X determines Z. Is this proof clear to everyone? Please tell me. Are you finding these proof very simple? Proving all these results is very simple, right? Just apply the direct proof, or you can apply the proof by contradiction. Okay. Please tell me, are you understanding these proof? Let me know. Quite simple. These are very intuitive and very simple proof. You can very easily prove all these things. Okay. Just go step by step. Just see what is given to you, and what you need to prove, and just apply the definition. Just use the definition. Very simple. So this is the proof of transitivity. So we have seen the proof of transitivity law. Okay. Very simple. So you can read this proof. The same proof we have seen. This proof we have already seen. Okay. So here you can notice, like for example, in this table, you can apply the transitivity law. For example, these two functional dependencies are given to you. Let's assume these two functional dependencies, these are given to you. Then by transitivity, what I can say, see, these functional dependencies, these are given to you. Title here determines studio name. Studio name determines studio address. So what transitivity says? The transitivity rule that says that this will determine this. Yes or no? This title here, this will determine studio address. Very simple. Okay, so this is the idea. So we have seen all these three rules. Please tell me, did you understand? Let me know. All the three rules we have seen, did you understand? Okay, so this is the idea. Now let me tell you that these three rules that we have seen, these are the rules. These are the rules that we have seen. These are called Armstrong axioms. Okay, what is the name? The name is Armstrong axioms. Now, why these are called Armstrong axioms? What is the meaning of axiom? Can anyone tell me? Can anyone tell me what is the meaning of axiom? Like in the probability subject, you study axiom. What that means? Axiom means that these are the basis. I can say axiom means these are the basis. These are the basis for all the results related to functional dependency. Okay, so remember, these are called Armstrong axioms. Armstrong axioms. What this means, let me know. This actually means that using these three rules, you can prove any rule related to functional dependency. Okay, means if you use these three, using these three, you can derive every theorem, every rule related to functional dependency. Anyway, that is not required. So I'm just telling you that these three rules, these are called Armstrong's axioms. Okay, and the proof we have already seen. Okay, we have already seen the proof. And these three rules, reflexivity, augmentation, transitivity, we call them Armstrong axioms. Okay, anyway, so let's move on now. Now let's see this law. Now, what we will do? Now we will see some more additional functional dependency laws. Some additional rules we are going to see. And that is, the first one is split on the RHS. Can you split on the RHS? What it means? It means that if X determines Y, Z, then can I say X determines Y, X determines Z? Can I say, tell me, if X determines Y, Z, can I say X determines Y, X determines Z? Can you prove it? Yes, this statement is true. See, this says that you can split on the RHS. You can split on the RHS. If I give you this functional dependency, then what this functional dependency means, you can split this functional dependency on the RHS. So if I give you that X determines Y, Z, then you can say that X will also determine Y, X will also determine Z. Is this clear? If I give you this functional dependency, then you can derive that this functional dependency will also hold, this functional dependency will also hold. Okay, so this is your split on the RHS rule. You can split on the RHS. Remember, we are splitting on the RHS. For example, if A1 to AN determines B1 to BM, then what you can do? You can split on the RHS. You can see we are splitting the RHS. This RHS we are splitting. Now, can you prove it? Can you prove it? Let's prove. Let's prove this, that we can split on the RHS. Okay, let's prove. So tell me how to prove it. You can again apply the direct proof. You can again apply direct proof. So tell me what is given. Just tell me what is given. Let me know. It is given that X determines Y, Z. This is given to you. And what you need to prove? Tell me what you need to prove. Just tell me what you need to prove. You need to prove that X determines Y and X determines Z. This is what you need to prove. Yes or no? Now tell me what you will do. Now you can apply the direct proof. What you can do? You can apply the direct proof. So if you want to apply the direct proof, then what you will do? For example, if you want to prove this X determines Y, then how to do that? You take two tuples with same X value. Yes or no? So very simple point. What you do? Take two tuples with same X value. Take two tuples with the same X value. With the same X value. And prove that those tuples will have same Y, Z value. Those tuples will have same Y, Z value. Okay, will have same Y value and same Z value. Okay, same Y value and same Z value. Is this clear? Tell me, same Z value. So can you take your copy pen and can you try? Can you try to prove it? Have you done it? Let me know. So remember, this is what you need to do. You take two tuples. In these two tuples, if I take same X value, okay, what I'm going to take? I'm going to take same X value. Same X value I'm taking. Now, I need to prove that this will be same and I need to prove that this will be same. These two values will be same. These two values will be same. This is what I need to prove. Okay, is this clear? So remember, I need to prove that these will be same. Like this value, this value. I need to prove that show these will be same. Show these will be same. Show these will be same. And and show that these will be same. Okay, show these will be same. Show these will be same. Is this clear? So this is what we need to do. And what is given to us? What is given to us? This is given to us that X determines YZ. This is already given to you. That if two tuples have same X value, then they will have same this combination. Okay, this combination will be same. So very simple point. If these two tuples have same X value, this is already given, remember, that X determines YZ. This means that if two tuples have same X value, then in those tuples, this combination will be same. Yes or no? In these two tuples, this combination will be same. Which combination? This combination will be same. For example, if you put BC here, the same combination you need to put here, BC. Okay, now can you notice? Hence proved. Now can you notice? Hence proved. Look at this. Look at this. Hence proved. Look at this. Look at this. Yes or no? Is this clear? So this is your proof. Okay, so very simple. Hence proved. So we have proved that. Hence proved. We have proved that X determines Y and X determines Z. Isn't it simple? Please tell me. Another very simple thing. So you can split on the RHS. On the RHS, you can split. If this is given to you, X determines YZ, then you can say X determines Y and X determines Z. So you can split on the RHS. Is this clear? Please tell me. Is this clear? Let me know. Now let me tell you another proof for this using Armstrong rules. Okay, can you prove it? See, this is a simple question. Prove this split on RHS. This split on RHS law. This rule you prove. Remember, we need to prove this split on RHS rule. We need to prove using these three, your Armstrong laws. Okay, so this is what we need to do. Now we need to prove this split on RHS. This rule we need to prove using Armstrong laws. So can we do that? Can we do that? Can we do that? See, what is given? Let me know what is given. It is given that X determines YZ. Okay. And what we need to prove? We need to prove that X determines Y. X determines Y, X determines Z. So tell me, this is already given to you. X determines YZ. Now tell me, you can only use these three rules. Either you can use trivial functional dependency, reflexivity law, or transitivity or augmentation. Okay. You can only use those three rules. Those three rules you can use. You can use Armstrong laws. So tell me how to do this. Please tell me. I need to reach here. Okay, this is where I need to reach. From here, I need to reach here. Is this clear? I need to go to X determines Y. So what I will do, very simple. See, just use the reflexivity. So using reflexivity, can I say YZ determines Y? Please tell me. Can I say this? This is your reflexivity. See, yes or no? This is your reflexivity, agree? Can I do this? This is your trivial functional dependency, right? This is your trivial functional dependency. Is this Armstrong law? Is this law of Armstrong? Please tell me. Is this law of Armstrong? Yes. Okay, so I'm only using the law of Armstrong. Now you can notice X determines YZ, YZ determines Y. So now using transitivity, what I can do? I can use the transitivity law. Just use the transitivity law. What I can do? I can say X determines Y. Yes or no? Is this clear? What I'm using here? I'm using transitivity, nothing else. I'm using transitivity. Please tell me this transitivity. Is this Armstrong law? Is this law of Armstrong? Yes. Yes. Okay. So hence proved. Hence proved. Isn't it simple? Okay. So you can see using Armstrong law also you can prove it. This is what I'm saying. See, I told you that Armstrong law. Why these three laws are called Armstrong law? Like why these three laws are special? These three laws, reflexivity, your transitivity and augmentation. Why these are special? Why these are so special? These are special because you can prove every other law using these laws. Is this clear? You can prove every other law using these laws. Okay. So this is the idea. So that is the reason. Now tell me how to prove X determines Z. How to prove X determines Z? Tell me. How to prove X determines Z? Let me know. Again, very simple. What I can do? I can do like this, that YZ determines Z. What is this law? Again, this law is reflexivity. Again, this law is reflexivity. Okay, yes or no? This law is reflexivity. Now what I can do? Now I can again apply the transitivity. Now I can again apply the transitivity. Okay, I can take this, I can take this. So if I again apply the transitivity, then what will happen? Then X will determine Z. This will happen because of transitivity. So that's it. So we have done this also, this also, this also. So X determines Y also, X determines Z also. Understood? Let me know. So we have proved that X determines Y also, X determines Z also. Please tell me, did you understand? So using Armstrong law also, you can do this. You can see. Using Armstrong laws also, you can do this. Okay. So remember these Armstrong law, why these are famous? Why these are famous? Okay. So let me tell you why these are famous. These Armstrong's laws, or I can say axioms. Why these are famous? These are famous because you can prove every other law using these laws. Okay. So these Armstrong axioms, first of all, what are these? There are three. Yes or no? The first is reflexivity. The first one is reflexivity. The second one, your augmentation. And the third one, that is your transitivity. Okay, these are the three laws. Now remember, these Armstrong laws, these actually, you can use these and you can prove any other law. So remember, all remaining laws can be proved using these. All remaining functional dependency laws, can be proven using Armstrong laws. Okay, so that is the reason these are special. These Armstrong laws, these are special because all other remaining laws you can prove using these Armstrong laws. Okay, is this clear? Tell me. Okay, is this clear? So actually, when this type of situation happens, then that is the reason these Armstrong laws, these are called sound. Okay, these are called sound. There is a word sound. So these are called sound. Anyway, that is not required for us. Okay, we don't care about it. So this is just a simple point. You can understand that all the remaining laws, all the remaining functional dependency laws, you can prove using Armstrong laws. Okay, that is the reason these Armstrong laws, these three laws are special, because using these three, you can prove every other law. Okay, understood? Let me know. Did you understand that these are special? Why these are special? Did you understand? Very simple. Now let's move on. But tell me one thing. In the GATE exam, if some question comes and they give you some rule, they give you, and they ask you, is this rule true or false? Will you use Armstrong laws to prove it, or will you use your direct proof? Please tell me, which proof will you use? In the GATE exam, if some new rule they give you, some MSQ question comes and they ask you which statement is true, which statement is false, then tell me, will you use these Armstrong laws, or will you directly use the direct proof? Just use the direct proof. Okay, just use the direct proof, because remember, if you use these, then it can become complicated. It can become very complicated. Okay, if you use these, so it can become very complicated. So just use the direct proof. Very simple. Okay, let's move on now. Now let's see this rule. Some more functional dependency laws. Now let's see this. Combining on the RHS. Can you combine on the RHS? Okay, now can you combine on the RHS? For example, if this is given that X determines Y and X determines Z, means X can determine Y also, X can determine Z also. Can I say X will determine YZ? X can determine Y, X can determine Z. Can I say X will determine this combination? Yes, this is true. Okay, if X determines Y and X determines Z, then X will also determine this combination. Can you prove it? Again, can you prove it? Let me know. Again, let's prove it. So what is given to you? Can you take your copy pen? These proofs are very interesting. Okay, all these proofs, these are very interesting. First of all, what is given? First of all, what is given to you? This is given that X determines Y and X determines Z. This is given to you. And what we need to prove? Tell me. What we need to prove? Let me know. We need to prove that X determines YZ. Okay, if you want to prove it, then what you can do, you can apply the direct proof. You can apply the direct proof. Okay, this direct proof, what this says? This says take two tuples with same X value. Okay, show that This says that show that if two tuples have same x value, then what they will have? If two tuples have same x value, then those tuples will also have same yz combination. Those tuples will also have same yz combination. Same yz combination. Yes or no? This combination. Okay, very simple. So can you do it? Yes, you can very easily do it. This is your x, this is your y, this is your z. Take two tuples with the same x value. Two tuples you take with the same x value. Now, can you prove that this combination and this combination, they will be same? First of all, what we need to prove? Remember, we need to prove that this combination is same. We need to prove these two are same. Okay, we need to prove this. Prove that these two are same. And what is given? And what is given to you? And what is given to you? This is given to you that x determines y and x determines z. This is given to you. Okay, very simple. This is given to you. So tell me, already this is given to you that x determines y. X determines y. This is already given to you. So because of this, what will happen? This is given to you, x determines y. So if two tuples have same x value, they will have same y value. If two tuples have same x value, they will have same y value. Yes or no? They will have same y value. Is this clear? They will have same y value. Now, similarly, remember, this is also given to you. This is also given to you that x determines z. What this means? This means if two tuples have same x value, they will have same z value also. Okay, they will have same z value also. So now can you notice? Now can you notice this combination is also same? Yes or no? Now can you notice this combination also has become same? This combination also has become same. So you can notice that x determines this combination. X determines this combination. Is this clear? Please tell me. Hence proved. Okay, very simple. I hope you are enjoying these proofs. These are very simple proofs. Just use the definition of functional dependency, nothing else. Okay, so you can split on the RHS and you can combine on the RHS. This is a note and this is important note. So on RHS, we can split and we can combine. Okay, we can split as well as combine on RHS. Is this clear? We can split and combine. We can split and we can combine on RHS. On RHS. Is this clear? Please tell me. We can split also, we can combine also. What this split means? Let me know. What this split means? When I say split on RHS, what this means? You can split on RHS, you can combine on RHS. Both of these things you can do. Both these things you can do. So tell me, split on RHS, what that means? This means that if x determines yz, then you can split on the RHS. You can split on RHS. Then x determines y and x determines z. You can split on RHS. And what this means? You can combine on RHS. What that means? That means that if x determines y and x determines z, you can combine the RHS. You can combine the RHS. Okay, x determines y, x determines z. You can combine the RHS, x determines yz. Okay, so you can split and you can combine on the RHS. Very simple point. Quite simple. Now let's move on. Tell me the answer for this question. Can we split on LHS? A very interesting question. Can we split on LHS? Can we split on LHS? What it means? It means if xy determines z, can we split on LHS? I'm asking, can we split on LHS? If xy determines z, then does it imply that x will determine z and y will determine z? Please tell me. Can we split on LHS? Means if this is given to you that xy determines z, then can I say that x will determine z and y will determine z? For this question, the answer is no. For this question, the answer is no. Okay. Why? Can you give me a counter example? Can you give me a counter example? Give me a counter example, I'm asking. Give me a counter example. Counter example means this type of situation I want. I want this type of situation that xy determines z, but x does not determine z. Okay, this type of situation I want. I want this type of situation that xy determines z, but x does not determine z. This type of situation I want. So can you give me? Yes, very easily you can create this situation. For example, this combination determines Z. Remember, this combination determines Z. If you repeat this combination, the value of Z will repeat. If you repeat this combination, the value of Z will repeat. Okay. But what can happen? Tell me. If now, is this the same combination? Is this the same combination? Please tell me. Is this the same combination? Are they same combination? They are not same combination, right? These two are not same combination. So what should be the value of Z? What should be the value of Z? Tell me, what should be the value of Z? This can be C, or this can be D, or this can be anything. Yes or no? For example, this can be E. Yes or no? So now you can notice, look at this situation. Please look at this situation. Here you can easily notice that XY determines Z. But can you notice X does not determine Z? Can you notice X does not determine Z? X does not determine Z. Yes or no? Is this clear? Please tell me. So very simple point that you cannot split on the LHS. You cannot split on the LHS. Give me this type of situation. XY determines Z, but X does not determine Z and Y does not determine Z. Can you give me this type of situation where this also does not determine Z, this also does not determine Z? Can you give me this type of situation? Yes, very simply, you can do this. What you can do, for example, I can do like this. 1, 2, 1, 2. Now here I can put the, see, if the combination is same, if this combination is same, okay, there can be more tuples. Remember, there can be more tuples. Here also you might be thinking, so there can be more attributes. Okay, if you are thinking like this, X, Y, Z, there can be some more attributes can be there. Is this clear? There can be some more attributes. For example, X, Y, Z, W, something like this. Okay, so there can be more attributes. You can do like this. Is this clear? Let me know. Like 1, 2, 3, something like this. So there can be more attributes. There can be more attributes. Okay, so you can say that, for example, 10, 11, something like this. Anyway, so you can see in these two tuples, XY value is same, XY combination is same. So the Z combination must be same. Of course, Z combination will be same. Okay, Z combination will be same. Now, can you create a situation that this will hold, but X does not determine Z and Y does not determine Z? Can you create this type of situation? Yes, I can do this. For example, what I can do like this: 1, 3, and I can put 4 here. No problem. Yes or no? 1, 3, I can 4 here. Similarly, what I can do this 2, 3, and I can put 5 here. Yes or no? Now, overall, you can easily see from this. Look at this and tell me what is happening. If you look at this, then what is happening? In this, you can easily see that XY determines Z. Okay, but you can see X does not determine Z and Y does not determine Z. Is this clear? So like this, you can create the counter example. So remember, you cannot split on the LHS. You cannot split on the LHS. Okay, so is this clear? So this is a note. This is a note. We cannot split. We cannot split on LHS. Okay, we cannot split FD on LHS. Okay, what this means? What this means, let me know. This means that, let me know what this means. This means that if XY determines Z, then we cannot derive. Then we cannot derive X determines Z. Okay, we cannot determine. So remember, we cannot derive X determines Z or Y determines Z. So these things we cannot derive. Is this clear? Let me know. So very simple. So you cannot split on the LHS. Remember, this is important. Can you give me a practical example? Can you give me a real life example? Anyone want to give me a real life example where XY determines Z, but X does not determine Z, Y does not determine Z? Can you give me a real life example where XY determines Z, but X does not determine Z and Y does not determine Z? Tell me, can you give me a real life example? For example, what you can do, this X can be pin code. See, this X can be pin code, and this Y can be house number. This Y can be house number. Okay, and this Z can be house location. This Z can be house location. Is this clear? See, now you tell me, if you know the pin code also and house number also, can you find the house location? Please tell me. Let me know. See, very simple point that if you know pin code I give you the pin code also. I tell you the pin code also. I also tell you the house number. Okay, pin code also I tell you. I also tell you the house number. Now, can you determine the location? Yes. Now you can reach the location, right? Okay, you can reach the location. But now you tell me, if I only give you pin code, can you reach the house location? Can you reach the house location? You cannot reach. Yes or no? Agree? Now tell me, if I only give you house number, I don't give you pin code. I don't give you pin code. If I only give you house number, can you reach? If I don't give you pin code, I only give you house number, can you reach? No, you cannot reach. Is this clear? Did you understand? So very simple point that you cannot split on the LHS. Okay, so remember, we cannot split on LHS. We cannot split FD on LHS. Is this clear? On LHS, you cannot split. So this is just a very simple real life example. You can check it out. Let's move on now. Can you combine on the LHS? Can you combine on the LHS? I'm asking, can you combine FD on the LHS? What it means? It means that if X determines Z and Y determines Z, X also determining Z, Y also determining Z, both of them are determining Z. Can you combine them on LHS? Does it imply XY will determine Z? Please tell me. X determines Z, Y determines Z. Can you combine on the LHS? We are saying that X determines Z. We are saying Y determines Z. Okay, from this, can I say that this combination XY will determine Z? This combination XY will determine Z? The answer is yes. Okay, you can combine on the LHS, no problem. This is answer is yes. Can you prove it? Can you prove it? Yes, you can combine on the LHS. On the LHS, you can combine. Let's prove it. Again, let's prove it. What is your proof? Just apply the direct proof. Just apply your direct proof. Tell me what is given. Let me know what is given. It is given that X determines Z and Y determines Z. What do you need to prove? What do you need to prove? Tell me. What do you need to prove? You need to prove that X, Y determines Z. This is what you need to prove. Okay, so what you will do? You can apply the direct proof. You can apply the direct proof. So what this direct proof says, take two tuples with same XY combination. What you will do? Take two tuples with the same XY combination. With the same XY combination. Okay, take two tuples with same XY combination and show that Z value will be same. And show that Z value will be same in those tuples. Z value will be same in those tuples. In those tuples. Is this clear? This is what you need to do. Agree with me? Just understand what you need to prove. You need to prove this. So what you will do? Take two tuples with same XY value and prove that in these tuples, Z value will be same. Okay, so what you will do? This is X, Y, Z or more attributes. There can be more attributes. Now, what we are saying take two tuples with the same XY value, with the same XY combination. Take two tuples with the same XY combination. For example, AB, AB. Now you prove that. What do you need to prove? You need to prove that this value, this will be same. Show it will be same. Show it will be same. Okay, so tell me, and remember, this is already given to you. It is already given to you that X determines Z and Y determines Z. This is already given to you. So you can easily see X determines Z, that also is enough. X determines Z, this is given to you. This is given to you that X determines Z. This itself is enough. Because X determines Z, what it means? If two tuples have same X value, they will have same Z value. Yes or no? If two tuples have same X value, they will have same Z value. Two tuples have same X value, they will have same Z value. Yes or no? Is this clear? Please tell me. Please tell me. Let me know. So that's it. Hence proved. So that's it. Hence proved. Okay, so very simple. So you can combine on the LHS, but you cannot split on the LHS. Is this clear? You can combine on the LHS. You cannot split on the LHS. There is no splitting rule for LHS. You cannot split on the LHS, but you can combine on the LHS. Is this point clear? So this is the final conclusion. Remember, you can combine on LHS. So on LHS, what you can do? For LHS of FD, on LHS of FD, what you can do? Tell me. On LHS of FD, what you can do? On RHS of FD, what you can do? Tell me. On LHS, what you can do, and on RHS, what you can do? Let me know. Let me know. So on LHS, you can combine. Yes or no? We can combine. We can combine. We can combine. But you cannot split. But you cannot split. On RHS, you can combine also. You can split also. You can combine also. You can split also. Okay. Understood? Is this clear? So quite simple. I hope you understood all these things. So quite easily you can do. So this is what we have seen. Tell me the answer for this question. This is statement, some more functional dependency laws. See, now in the GATE exam, what they can do? They can give you this type of statement they can give you. They can ask, is this statement true or false? So tell me, this statement, is this true or false? If A determines B, BC determines D, then can I say AC will determine D? Can I say AC will determine D? A determines B, BC determines D. Now I'm asking, can I say AC will determine D? Can you prove it? This statement is actually true. This statement is true. Can you prove it? Just take your copy pen and try to prove it. Can you prove it? See, very simple. A determines B. See, remember, A has the power to determine B. A has the power to determine B. Who is more powerful? Who is more powerful? A or B? Who is more powerful? A has the power to determine B. Who is more powerful? Tell me. A simple question I'm asking. A simple question I'm asking that if, okay, this is just an analogy, nothing else. This is just an analogy. This is just an analogy. Tell me, district is more powerful or state? District or state in functional dependency terms, in the terms of functional dependency. See, which is more powerful, state or district? Which information is more powerful? I'm asking you, which information is more powerful? I tell you what is the state. I tell you what is the district. Okay, let's assume this is a very thriller movie. Okay, some thriller movie is going on, and you ask someone, you are the police, you are the Singham. Okay, you ask someone, where is the criminal? Okay, they give you the state name. They tell you Maharashtra. Is that information more powerful, or if they tell you Mumbai? Tell me. So which information is more powerful? Mumbai, yes or no? That information is more powerful. So remember, this is analogy. This is just an analogy that if you have this FD you have X determines Y, then this is just an analogy that X is more powerful than Y. Okay, we can think, you can think like this. You can think like this, that X is more powerful than Y. Because X can determine Y. X is more powerful than Y. Okay, X is more powerful than Y. Remember, this is just an analogy. This is not a concept. Is this clear? This is just an analogy. This is not a concept. This is not a concept. I am just telling you the analogy that you can think like this, that X is more powerful than Y because X can determine Y. Okay, here you can see that X value can determine Y value. X value can determine Y value, but Y value cannot determine X value. X value can determine Y value. Okay, so you can think like this. Now you can easily see it's like this. A is more powerful than B. BC is more powerful than D, but A is more powerful than B. See, BC is more powerful than D. This BC is more powerful than D, but A is more powerful than B. But A is more powerful than B. So from this, what I can say? Can I say AC will be more powerful than D? Please tell me. See, very simple. This is just an analogy that BC is more powerful than D. A is more powerful than B. This A is more powerful than B. Instead of this B, you are putting A. Yes or no? Instead of this B, you are putting A. So, of course, this AC is more powerful than BC. Yes or no? AC is more powerful than BC. Is this clear? Please tell me. AC, that is more powerful than BC. So very simple. So this is how you can do. But anyway, let me give you the formal proof. Let me give you this proof. So remember, let me give you proof number 1. That is using Armstrong law. Using Armstrong law, can you prove? Using Armstrong laws, can you prove? Tell me. Can you prove using Armstrong laws? Let me know. This same statement can you prove using Armstrong law? What do you need to prove? First of all, what do you need to prove? You need to prove that this, that AC determines D. AC determines D. And what is given to you? And what is given to you? It is given to you that A determines B and BC determines D. Yes or no? So tell me, how can you use Armstrong law? You can use augmentation. From here, can I use augmentation? Can I use augmentation and can I say AC determines BC? This law, what this law is called? This is your augmentation. Agree? Agree. This is your augmentation law. So you can apply the augmentation law. Now what you will do? Now you can apply the reflexivity law. What you can do? You can apply the reflexivity law. BC. Oh, okay. This is already given to you that BC determines D. This is already given to you. Okay, this is given to you. Now, from these two, you can apply the transitivity. So if you apply the transitivity, what you will get? You will get AC determining D. Understood? Let me know. See, very simple point. This is given to you, A determining B. You can apply augmentation law. You will get AC determining BC. This is your augmentation law. Okay. Now, this is already given to you. BC determining D. This is given to you. So you can apply the transitivity and you will get AC determining D. This is your proof number 1. Now, can you prove it using direct proof? Tell me. This is already given to you that A determines B and BC determines D. Can you prove using direct proof? What do you need to prove? You need to prove that AC determines D. Okay, so you can apply the direct proof. Very simple. This direct proof you can apply. Okay, and in this direct proof, what will happen? Let's assume A, B, C, D, E. These are the attributes. Okay, what you will do? You will take two tuples, T1, T2. Which value you will keep same? Which value you will keep same? Tell me. Which value you will keep same? Which value you will keep same? You will keep AC value same. See, you need to prove this. So focus on AC. You will keep AC value same. You need to prove AC determines D. Please focus on this. What you need to prove? Focus on that. What you need to prove? Focus on that. You need to prove that if two tuples have same AC value, then they will have same D value. Is this understood? You need to prove that if two tuples have same AC value, they will have same D value. So you take same AC value. Okay, let's take same AC value. For example, let me put A here, B here, A here, B here. I am taking same AC value. I am taking same AC combination. This AC combination I am taking same. Now, what is given to you? A determines B. A determines B. So if two tuples have same A value, they will have same B value also. Yes or no? They will have same B value also. Agree? Now tell me, this is given to you. BC determining D. If two tuples have same BC combination, then they will have same D value. Hence proved. Okay, hence proved. Now you can see that AC determines D. Now here you can easily see that AC determines D. So this is your direct proof. So focus on what you need to prove. Okay, so remember, you need to prove that if two tuples have same AC value, then they will have same D value. So you start from this. Take two tuples with same AC value. This is your starting point. Agree? This is your starting point. Take two tuples with same AC value. This is your starting point. Then use these things which are given to you. These things are given, use, and then finally you will get your result. So we have seen this. Very simple. I hope you can do all these things. Can you tell me the answer for this? This statement is true or false? A determines B, C determines D. Then can I say AC will determine BD? Can you use analogy? See, this statement is also true. What about analogy? What about analogy? Just think about the analogy. What is the analogy? Analogy is like this. See, A is more powerful than B. C is more powerful than D. So can I say AC will be more powerful than BD? See, A is more powerful than B. C is more powerful than D. this is more powerful than B. This is like Ambani. Okay, maybe this is like Amitabh Bachchan. Okay, and this is maybe some politician, and maybe this is some normal employee. Okay, so you can see that A is more powerful than B, C is more powerful than D. Then ultimately, can I say that this AC will be more powerful than BD? Anyway, this is just an analogy. Tell me, in the GATE exam, if some question will come, will you use analogy? Don't use analogy. Okay, analogy is just for remembering purpose. Analogy is not a proof. Analogy is not a proof. Don't use analogy. This is just for remembering purpose. Okay, once you prove it, then how can you remember it? This is the point. Once you prove it, first you prove it. Give a correct proof. So first you prove it, then how can you remember it? For that, analogy is helpful. Okay, so tell me here. Now tell me. So you can see A determines B, C determines D. So here, can you prove that AC will determine BD? Can you prove AC will determine BD? Yes. Again, you can apply the direct proof. Okay, what you can do, you can apply the direct proof, you can apply, or you can use the Armstrong laws. You can also use the Armstrong laws. That is also fine. Okay. If you want, you can use the Armstrong laws also. Okay. So anyway, so let's apply the direct proof. Let's apply the direct proof. That is quite simple. See, the direct proof is actually very simple. What you need to prove? You need to prove that AC determines BD. AC, BD. Okay, some other attributes can be there. Okay, you need to prove. So tell me, what will be your starting point? You just tell me that. What will be your starting point? Let me know. Your starting point will be what? If two tuples have same AC value, then they must have same BD value. So you take two tuples with same AC value. Take two tuples with the same AC value. Take two tuples with the same AC value. Okay. Now tell me. So this is your starting point. This is just the starting point. Remember, this is your starting point. I can say this is the starting point. Now you tell me, this is given. A determines B. So if two tuples have same A value, they will have same B value. If two tuples have same A value, they will have same B value. Now, this is given. C determines D. If two tuples have same C value, they will have same D value. That's it. Hence proved. Hence proved. Okay, yes or no? Now, can you notice hence proved? Isn't it simple? The direct proof. Do you need to use too much, I can say, fancy analysis? Please tell me. Do you need to do some fancy analysis? Some clever analysis? Nothing. This is very simple thing. This direct proof is very simple. Just apply the direct proof. Very simple. You don't need any fancy analysis. Okay. So this is the idea. I hope you understood. So this statement is also true. Now let's move on. Tell me this statement. Is this true or false? If A determines B, then can I say B determines A? This statement is false. This statement is false. Can you give me a counter example? Can you give me a counter example? Let me give you a counter example for this. For example, I can say that IFSC code. If you know the IFSC code, then you can determine what is the bank name. But you can see the bank name does not determine IFSC code. Yes or no? Very simple. So this is your counter example. Okay. So remember, functional dependencies are one way. Yes or no? Can I say from this, can I say that functional dependencies are one way? From this, I can say that functional dependencies, FDs are one way. Yes or no? FDs are one way. One way. If you say that A determines B, this does not mean that B determine A. Okay. FDs are one way. Is this clear? If you say A determine B, this does not mean that B determine A. So quite simple. So we have seen all these things. Okay. Be careful. Don't split on the LHS. Here you cannot, this is given to you, that don't split on the LHS. This is a very common mistake. If this functional dependency is given to you, you can see if this is the given functional dependency, then don't split on the LHS. If this is the given functional dependency, then don't say that A determines C. Don't say B determines C. So don't split on the LHS. Is this clear? Please tell me. Let me know. So all these rules we have seen. All of them we have seen. You can check it out. Okay. If something is missing, are you confident that you can prove it? We have already seen all of them. This reflexivity, augmentation, transitivity, these we have seen. All these also we have seen. Are you confident you can prove it? These names are not important. These names are not important, but these names are important. Okay, is this clear? If you are thinking which names are important, see, only these names are important. Only these names are important. The remaining names, these are not important. Okay, these remaining names, these are not important. You don't have to remember. But these, the first three, these are important. Why? What is the reason first three are important? Because these are Armstrong laws. These are the axioms of Armstrong. Armstrong axioms. So these are important. These names are also important. The remaining names are not important. So you don't have to remember the remaining names. Okay, don't by heart the remaining names. Anyway, let's move on. Now let's see this point. Trivial functional dependencies, are they interesting? Trivial functional dependencies, are they interesting? Please tell me. They are not interesting because they are always, see, they will always hold. Yes or no? Trivial functional dependency will always hold in every instance of every relation. Whatever instance you take, whatever relation you take, trivial FDs always will hold. So they are not useful. They are not useful, okay, in study. Okay, when we study functional dependencies, then they are not useful and they are of little interest, I can say. So remember, non-trivial functional dependencies are interesting. Non-trivial functional dependencies, they are interesting and they are useful. Okay, one more thing. If a non-trivial functional dependency is given to you, can you remove the trivial part from it? If a non-trivial functional dependency is given to you, then can you remove the trivial part from it? See what I'm saying. If a non-trivial functional dependency is given to you, you can split the RHS, you can remove the trivial part, and then you will get a completely non-trivial FD. Yes or no? If I give you some non-trivial FD, let me give you a non-trivial FD. I'm giving you this non-trivial FD, for example, AB determining BC. This non-trivial FD I'm giving you. Is this non-trivial? Yes, this is non-trivial. Is this completely non-trivial? Is this completely non-trivial? Please tell me. This is non-trivial, but is this completely non-trivial? This is not completely non-trivial, right? Yes or no? This is non-trivial, but this is not completely non-trivial. Now tell me, how to convert this to completely non-trivial? Let me know. You already know you can split on RHS. See what you can do. You can split on RHS. You can split on RHS. You can split. So if you split on RHS, what you will get? What you will get? You will get this and you will get this. Agree? Is this clear? You will get this. Can you notice this is the trivial part? Can you notice this is the trivial part? This is the trivial part. And this is the completely non-trivial part. And can you notice this is the completely non-trivial part? Completely non-trivial part. Understood? Is this clear to everyone? Please tell me. Okay, so very simple point. This is what I'm saying. Non-trivial functional dependencies are interesting. In a non-trivial functional dependency, if I give you non-trivial functional dependency, you can split the RHS, you can remove the trivial part because trivial part is not important. Trivial part is not useful. Okay, so you can remove the trivial part and you can get completely non-trivial FD. Is this understood? Please tell me. So if I give you this non-trivial FD, you can see this is non-trivial FD because LHS is not superset of RHS. Okay, but this is not completely non-trivial. This functional dependency, this is not completely non-trivial. So what you can do, you can split on LHS. If you split on LHS, you will get this trivial part. This is the trivial part and this is the completely non-trivial part. So this is what I'm saying. Is this clear? And this is interesting and this will be important. This will be important. Okay, now let's move on. Now we need to study the next concept, that is closure of a set of attributes. This concept we need to study and this is very important concept. But before we start this concept, did you understand everything that we have done so far? Did you understand what is functional dependency? What are the laws of functional dependency? How to prove laws of functional dependency? What are Armstrong axioms? Everything so far. Are you confident in the functional dependency? Please tell me. Are you confident? Let me know. A student is asking, sir, in this case, only know when A determines B, but B does not determine A. In FD lecture, you gave example. See, we cannot guarantee, right? It is possible. Okay, let me tell you what the student is asking. Okay, so this is student doubt. Is it possible? This is what I'm asking. Is it possible? Please tell me, is it possible that A determines B and B determines A? Is it possible? I'm asking, is it possible? Is it possible that A determines B, B determines A? Yes, it is possible. But will it happen? Will it always happen? See, is it possible that this happens? The answer is yes. The answer is yes. The answer is yes. Now you tell me. Now you tell me. But if I tell you this statement, now consider this statement as one. I am giving you this statement that if X determines Y, then Y will determine X. Is this statement true or false? But tell me, if I give you this statement, is this statement true or false? Is this statement true or false? Can I say this statement is true? Can I say this statement is true? No, this statement is false. Okay, tell me, this false, does it mean it will never happen? False, does it mean it will never happen? When I say false, does it mean it will never happen? No. Okay, it may or may not happen. It may or may not happen. For example, in mathematics, let's come back to mathematics. Let's come back to mathematics. In mathematics, can I say that A plus A, that will be A square? This statement is true or false? Tell me. This statement is true or false? Please tell me. This statement A plus A is equal to A square in mathematics. This statement is false. But can I say it will never happen? Does a false means never happen? Does false mean never happen? Can I say it will never happen? It can happen, right? It can happen. For example, 2 plus 2 is equal to 2 square. So remember, false does not mean that it will never happen. Okay, false does not mean that it will never happen. Is this understood? Please tell me. So remember, is it possible A determine B, B determine A? Is it possible? Yes, it is possible. But can I say that if X determine Y, then Y will determine X? This statement is false. Okay, is this understood? Please tell me. Okay, very simple. Now let's move on now. Now let's see closure of a set of attributes. This is very simple and interesting topic. What is this concept? Closure of set of attribute. Now, let's assume you have a relation schema. Let's assume you have a relation R. This relation R you have. In this relation R, on this relation R, some functional dependencies are defined. Okay, some functional dependencies are defined. FDs. Okay, the set of FDs are defined. Let's assume set of functional dependencies are given to you. Set of functional dependencies S on R. Let's assume that is given to you. Okay. Now, let's assume that X is a subset of R, means X is set of attributes. Let's assume this X, this is a set of attributes. Let's assume this is set of attributes. Okay. This X, this is set of attributes. Then what is closure of X? Now, in this situation, remember, X is set of attributes and this is your functional dependency. These are given to you. So two things are given to you. Functional dependencies are given to you and this X is set of attributes. This is given to you. Now, what is closure of X? Let's see what is closure of X. What this concept? Closure of X. We will denote it like this. We can denote it X plus. This is how we denote. Okay, some people can denote it X star, but most of the time it will be denoted X plus. Okay, so this is how we denote. So closure of X, we denote X plus. What this means? This means all the attributes which X can derive. Let me tell you, this means, what this means, this will be equal to set of all attributes. Set of all attributes which X can derive, which X can determine. Is this clear? Please tell me. Okay, so remember, this is set of all attributes which X can determine. Very simple point. Closure of X means the set of all attributes which X can determine. What are the attributes which X can determine? X can determine. So how can you write it? You can write like this, that the closure of X, the closure of X, closure of this X, we denote by X plus. That is equal to, that is set of attributes. Remember, that is set of attributes. Okay, those attributes you take which you can derive from X. Those attributes you take, this Y is an attribute. Okay, this Y is an attribute. You take all those attributes which X can determine. Okay, which X can determine. Is this clear? So if X can determine Y, then you put this in the closure of X. Very simple point. So the definition is very simple. Closure of X means all the attributes which X can determine. Set of all the attributes which X can determine. Okay, set of all the attributes which X can determine. X can determine Y. All those Y you put here. This is your closure of X. Very simple point. I hope you understood. Now let's take some questions. For example, let me give you some functional dependencies. This functional dependency set I'm giving you, let's assume. For example, A determining B, B determining C, and D determining B. Okay, let's assume this is given to you. This set of functional dependency is given to you. Now tell me, what will be closure of A? This functional dependency set, this is given to you. What will be closure of A? I want closure of A. Which are the attributes A can determine? Please tell me. What is the closure of A? Can I say A will determine A? Please tell me. Can I say A will determine A? Yes. By reflexivity? Yes or no? By reflexivity, can I say that A will determine A? Agree with me? So I can say A will determine A. So in A plus, I will put all those which A can determine. So can I put A? Can I put A? Can I start with A? Yes. Yes or no? So you can notice A can determine A. So I can put A here. Very simple. What else? What else? Tell me, what else? You can notice A can determine B. This is given. A can determine B. This is given. This is given. So you can put B also. You can put B also. Yes or no? What else I can put? What else I can put? Notice transitivity. From transitivity, you can see that A determines B, B determines C. Then what transitivity says? What transitivity says? Please tell me. From here, what transitivity says? You know. So by transitivity, you already know the rule of transitivity. By transitivity, can I say A determines C? Can I say A determines C? Please tell me. See, A determines B, B determines C. So by transitivity, I can say A determines C. So because you can determine C, put C also. Put C also. Can you determine something else? Can you determine something else? Can I determine D? From A, start from A, can you reach D? If you start from A, you start at A. Okay, let's assume you are starting at A. If you start at A, you can reach A, you can reach B. Transitively, you can reach C, but you cannot reach D. Agree with me? Is this clear? Please tell me, did you understand? If you start at A, then you can reach C. What is happening here? This is happening. I want A closer. This is what I want. This is what I want, right? So what I will do, I will start at A. This is where you start. Start at A. Okay. Reflexivity. Reflexivity means that A will determine A. Yes or no? Reflexivity. By reflexivity, A will determine A. This is given to you that A will determine B. This is given to you. This is given to you that A will determine B. And this is given that B determines C. So transitively, A determines C. So transitively, A determines C. But you cannot reach D. Yes or no? You cannot determine D. Is this understood? Please tell me. So this is your set of all attributes A can determine. This is set of all attributes. These are the attributes. This is set of all attributes A can determine. Is this understood? Did you understand the concept of closure? What the concept of closure? Did you understand? So this is set of all attributes that A can determine. Understood? Now, tell me the next. In the same question, if I ask you, what is the closure of B? What is the closure of B? Tell me. What is the closure of B? What things B can determine? See, B can determine B. Why? This is your reflexivity. This is your trivial functional dependency. This is your trivial functional dependency. You already know. Trivial functional dependency will always hold. Trivial functional dependency will always hold. You already know this. See, this is your trivial functional dependency. This is a trivial FD. Okay, and remember, trivial FDs, they always hold. They are always, they will always hold. They will always hold in every relation. So B can determine B. So I can say in B plus what I will do, I will start with B. Then what I will do, you can notice B will determine C. This is given to you. This is given to you that B determines C. So you can put C also. Can you put something else? Can you put something else? No, you cannot put anything else. Yes or no? You cannot put anything else. So if you start at B, what you can do? Notice you start at B, you can put B, you can put C, but can you determine something else? You cannot reach D, you cannot reach A. So this is the simple point. Is this understood? In the same question, you tell me, what is the closure of BD? What is the BD closure? Now I'm asking this BD, what BD will determine? Okay, now what this BD will determine? This pair. Now this pair is searching. This pair is searching what we can determine. Okay, now they are together. They are searching what we can determine. Yes or no? Yes or no? They are searching what we can determine. Together what we can determine. So what will happen? You can easily see that. Can I say BD will determine B? Please tell me, can I say BD will determine B? Can I say BD will determine B? Yes, of course, by reflexivity. By reflexivity, this is your transitive functional dependency. By reflexivity, do you agree? Did you understand that BD will determine B? What is the reason? What is the reason BD determines B? That is your trivial functional dependency. Yes or no? Tell me, can I say BD will determine D? Can I say BD will determine D? Yes, BD will determine D. Again, this is your trivial FD. Again, this is your trivial FD. Okay, yes or no? Trivial FD will always be true. Trivial FD will always hold. Okay, what else we can do? What else we can do? Tell me, what else we can do? Notice transitivity. See, notice. BD determines B. B determines C. Transitively, what you can say? Transitively. Tell me, transitively, what I can say? Transitively, what I can say? Use transitivity. Then BD determines C. Do you agree? BD will determine C. Use transitivity. BD can determine B. B can determine C. So BD will determine C. Yes or no? So BD will determine C. Is this clear? So this is your transitivity. What else? What else we can put? Let me know. Can I put something else? Can I put something else? Only A is remaining. Can I put A? Can I derive A? I cannot derive A. Yes or no? I cannot reach A. If I start at BD, I cannot reach A. Is this clear? You cannot determine A. So that's it. So this is the set of attributes you can determine. Is this clear? This is your BD closure. This is your BD closure. Is this clear? This is the set of attributes. This is the set of attributes this BD can determine. This BD can determine. Is this understood? Please tell me. The concept, did you understand? Okay. Is this clear? The small points, are you understanding? That what is happening? Transitivity, reflexivity, all these small points, are you understanding? What is happening? Now let's move on. Tell me what this AC will determine. What this AC will determine. What is the closure of AC? Tell me, what is the closure of AC? Now you can do it quickly. Okay, you can do it quickly. See, if you start at AC, AC will determine AC. What is the reason? Give me the reason. Why I can put directly AC? AC will determine AC. Why? AC will determine AC by reflexivity. AC will determine AC by reflexivity, by transit, by your trivial functional dependency. Yes or no? By your trivial functional dependency. This is your reflexivity. So AC will determine AC. What else? A itself can determine B. Yes or no? See, together what they can bring. Yes or no? You are thinking that together what they can bring together. This A itself can bring B. So of course together they can bring. Yeah, agree or not? See, just think like this. Just do the visualization. See, we do the visualization. This AC, what they can bring together. Together what they can bring. Now you can notice A itself can bring B. This A itself can bring B. So of course AC also can bring B. Yes or no? Is this clear? Is this clear? Please tell me. So very simple. So B also will come. What else will come? What else will come? Can you bring D? Can you determine D? No, you cannot determine D. Yes or no? So that's it. So this is your answer. I hope you understood the concept of closure. So remember, if you have a set of functional dependency, a set of functional dependency is given to you. This set of attributes is given to you. Set of attributes. Then what is closure? What is closure of X with respect to this functional dependency? Closure of X with respect to this functional dependency, that will be This is how we denote it. We can denote like this, x plus, and this is a set of all attributes which x can determine. Yes or no? Set of all attributes which can be determined by x. So this is the concept of closure. Tell me the answer for this question. Let me know. For the given set, this set of FDs are given to you. This is the set of functional dependencies. Set of functional dependencies given to you. The question is asking closure of A. With respect to these functional dependencies, what is the closure of A? What A can bring? Just tell me. I am asking what A plus, what is the closure of A? Can I say A will bring A? Can I say A will bring A? You can start at A. Why? What is the reason? A will bring A. What is the reason? Because of reflexivity. Because of reflexivity. Anyway, now tell me the next. A can bring A. Okay, this is already given that A can determine B. So you can put B also. You can put B also because A can determine B. You can put B also. This is given to you. This is already given to you. Okay, what else? What else A can determine? Transitively, you can see A can determine C also. Notice, A can determine B, B can determine C. Transitively, A can determine C also. So you can put C also. Transitively, A can determine C. So I can put C also. Yes or no? A can determine C. Agree with me? What else? What else? What else? Tell me. Now notice. A can determine BC. Yes or no? Can you notice A can determine BC? Yes or no? So far, what we have done? So far, we have done that A can determine BC. You can see here that A can determine BC. Yes or no? You can see A can determine BC. And what BC can determine? A can determine BC. What BC can determine? Tell me. A can determine BC. What BC can determine? BC can determine D. BC can determine D. So what transitivity says? Transitivity says that A can determine D. That's it. Did you understand this? Please tell me. See what I'm saying. A can bring BC. Okay, A has the power to bring BC. And this BC can bring D. Yes or no? So what A will do? First A will bring BC. Then this BC can bring D. Just think logically. Yes or no? A is so powerful that this A can bring BC. And then this A can tell, okay, now bring D. Now they can bring D. Yes or no? Is this clear? Please tell me. Let me know. Understood? So A can bring everything. A can bring everything. A can determine A, B, C, D. A can determine A, B, C, D. A can determine everything. Is this understood? Please tell me. Did you understand the concept? Let me know. Now, in the same question, I can ask you some more variations. For example, what the closure of AB? Or maybe I can ask you what the closure of BC? Tell me, what is the closure of BC? I am asking you what the closure of BC? Tell me, what will be the closure of BC? What BC can bring? See, BC can bring BC by reflexivity. That you already know. That you already know. BC can bring BC. You can start here. That will happen because of reflexivity. Because that is a trivial functional dependency. You already know. Okay, so this will happen because of reflexivity. Trivial functional dependency. Now, this B itself can bring D. See, okay, this BC can bring D also. From here, BC can bring D also. This is given to you. Okay, so you can bring D also. What else? Can you bring A? Can you bring A? Can you bring A? No, you cannot bring A. So this is your BC can determine BCD. So remember, BC can determine BCD. Nothing else. Very simple. Understood? So quite simple. Okay, so this is given. I hope you understood all these things. Okay, so you can do whatever variation you want, you can do. For example, what about CD plus? What about CD plus? Tell me. Tell me, what about CD plus? I want to know what is CD plus. So you can see CD will determine CD. You can bring CD. Okay, CD you can bring. Now tell me, what else they can bring? What else they can bring? Now CD are standing. They are thinking what we can bring. What we can bring. They can bring CD. But what else they can bring? What else they can determine? Nothing else. Yes or no? Nothing else. So CD can determine CD plus, that is equal to CD. Or I can say CD can only determine CD. That's it. CD can only determine CD. Nothing else. Nothing else you can determine. Okay, very simple. Tell me the answer for this question. This question is taken from Ullman. What is the answer for this question? Let's consider the relation with attributes A, B, C, D, E, and F. So this relation is given to you. Okay, this relation is given to you, which has A, B, C, D, E, F, these attributes. Now the question is asking, remember, these are the attributes that are given to you, A, B, C, D, E, F. Now the question is saying, these functional dependencies are given to you. Okay, remember, these functional dependencies, this FD set is given to you. What is the FD set? This is AB determining C, BC determining AD, D determining E, CF determining B. Okay, this is the set of functional dependency that is given to you. What is the closure of AB? What is the closure of AB? Means AB plus. Tell me, what will be the closure of AB? Let's find out. What will be the closure of AB? What AB can bring? Tell me. See, AB can bring AB. That is very simple. You can start with AB. AB can bring AB because of reflexive property, reflexivity, trivial functional dependency, trivial FD. So AB can bring AB. There you can start. What else AB can bring? They are thinking what we can bring. They are thinking, okay, we have power of 2. Yes or no? We together, what we can bring to the table. So tell me, you can see AB can bring C. Yes or no? You can notice AB can bring C also. Now these three, what they can bring? Okay, please understand. Now these three, what they can bring? Now team is growing. Yes or no? Team is growing. You started from here. Okay, you started from here. Then team is growing. This AB can bring C. Now these three people, what they can bring? These three people, what they can bring? Tell me, what they can bring? These three people. You can notice this BC can bring AD. Yes or no? Please notice this BC. Okay, notice what I'm doing. This BC can bring AD. Okay, this BC can bring AD. So D has also come. D has also come to the party. Now what these four people will bring? Now what these four people will bring? Tell me. Now you can notice this D can bring E. So E also has come to the party. Yes or no? Now these five people, what they can bring? These five people, what they can bring? Can they bring F? No, they cannot bring F. Yes or no? They cannot bring F. So that's it. Is this clear? So this is your AB closure. Did you understand? Please tell me. So AB closure, I can say AB can determine A, B, C, D, E. Okay, is this understood? Tell me one thing, a simple question I'm asking. This is your AB closure, that is A, B, C, D, E. Okay, we found. So can I say this statement will be true? Can I say this statement will be true if I give you this? Is this statement true or not? Is this statement true or not? If this statement is given to you, this statement is true or not? Please tell me. In the exam, if they give you this statement, MSQ question is there, this statement is true or not? This statement is false. Why? Because remember, when I say X closure, what that means? Please understand, X closure is a set of all attributes which X can determine. Set of all attributes which X can determine. Which X can determine. Is this clear? Which X can determine. You must take all the attributes which X can determine. Is this understood? Please tell me. Okay. So remember, in the GATE exam, if they give you this is not true. But if they give you this, is this true? In the options, if this is given, is this true? In the options, if this is given, is this true? Yes, this is true, right? Because this is not a closure. This is functional dependency. Yes or no? Is this clear? This is not closure. Are we talking about closure here? Are we talking about closure here? Please tell me. Are we talking about closure? No. This is just a functional dependency. This is not closure. This is just a functional dependency. Is this clear? This is just a functional dependency. Just a functional dependency, not closure. Okay, understood? This difference, did you understand? Okay, here we are finding the closure, and this is just a functional dependency, not a closure. Okay, so quite easily you can do all these things. Tell me one thing, in this question, forget about the question. Now you tell me, who has the power to bring F? If you want to determine F, who has the power? Which attribute has the power to determine F? Please tell me. Which attribute has the power to determine f? To determine f, which attribute? Tell me which attribute has the power to determine f? F itself, no one else. Yes or no? Remember, if you want f, if you want to determine f, can you notice? Can you notice if you want to determine f, then what must be here? This is my question. Please understand my question. Please understand my question. This is the question. This is my question, that if I want to determine f, then what should be here? I can guarantee that you must have superset of f here. Yes or no? Okay, whatever you put here, that must contain f. Whatever you put here, this must contain f. This must contain f. Do you agree? This must contain f. Do you agree with me? If you do not contain f, okay, you can take all the remaining attributes, they cannot determine f. Okay, if you, even if, for example, okay, tell me what the closure of A, B, C, D, E. Tell me what the closure of A, B, C, D, E. Let me know. What the closure of this A, B, C, D, E? A, B, C, D, E. What the closure? The closure is also A, B, C, D, E. They cannot determine f. No one has the power to determine f. Only f can determine f. Yes or no? No one has the power to determine f. You can see no one can determine f on the RHS. Look at the RHS. Look at the RHS. Look at the RHS. No one can determine f. Only f can determine f. So can I say that whatever you put here, that must contain f? Whatever you put here, that must contain f. Whatever you put, you can put AF. That is fine. You can put AF. You can put CAF. You can put whatever you want, or you can put only f. But whatever you put, this must contain f. Okay, understood? Now let's move on now. So tell me the answer for this question. The question is asking, for this x, what is the closure? What is the closure of x? What is the closure of x? Tell me. Let me know. So this question is given to you, and the question is asking, what is the closure of x? X is CID. Okay, your x, what is that? That is your CID. Now the question is asking, what is the closure of x? What will be the closure of x? Of course, CID you will put. Yes or no? What else you will put? Tell me. Of course, you can put CID. What else you can put? What this CID can bring? What this CID can bring to the table? This CID can bring title. CID can determine title. Yes or no? CID can determine title. Okay, this CID, this can determine title. Now tell me. Now these two people, what they can bring? Okay, remember, family is growing. Yes or no? The group is getting stronger. The family is growing. Okay, initially you have CID. Now these two people, what they can bring to the table? Now these two people, they will bring to the table. So tell me. Now you can notice title can determine department. This title can bring department. You can bring department also. Yes or no? Now these three, what they can determine? Family is growing. Yes or no? Now these three, they will work hard and they will bring something new. They will try to bring something new. Can you bring something new? These three people, what they can bring? CID title department. CID title department. What they can bring? They cannot bring anything else. Can they bring year? This year can they bring? Tell me, can they bring year? No, they cannot bring. Yes or no? Is this clear? So that's it. So that's it. So this is your answer. So remember, this year, this does not belong to X plus. Agree with me? Agree with me? This year does not belong to X plus. Okay. Look at this and tell me, who has the power to bring year? Who has the power to bring year? Tell me. Look at this set of functional dependency and tell me, who has the power to determine year? You can notice no one can determine year. Look at the RHS. You don't have year. Do you have year on the RHS? On the RHS, do you have year? On RHS, you don't have year. On RHS, we don't have year. We don't have year. Okay, so no one can determine year. Only year can determine year. Yes or no? Is this clear? So remember, if something determines year, okay, if something determines year, then this must contain year. Yes or no? Then this must contain year. Is this clear? Because on the RHS, we don't have year. So no one can determine year. on the RHS, we don't have year. So no one can determine year. Only year can determine year. So we must contain year if you want to determine year. Okay, let's move on now. What is the closure of CID comma year? Please tell me. In the same question, I am asking what is the closure of CID comma year? See, CID can determine everything else, but year it cannot determine. Okay, now CID comma year, they can determine everything. You can check it. Okay, finally you will get everything. This you can do it. Very simple. Tell me the answer for this question quickly. You have become expert. Tell me the answer for this question. What is AB closure? Set of functional dependencies are given to you. This is the schema. A, B, C, D, E, F. These are the functional dependencies. So tell me what is AB plus? Okay, I can also write it AB plus. These things are same. So tell me what that will be. So you can notice you can start with AB. AB can bring AB. Okay, now these two people, what they can bring? These two people, what they can bring? See, AB can bring C also. AB can bring C also. Now these three people, what they can bring? These three people, what they can bring? You will notice these two people can bring D. Yes or no? These two people, look at these two people, they can bring D. They can bring D. What else? Now these four people, what they can bring? Family is growing. Okay, the group is getting stronger, bigger. So tell me what they can bring. Tell me. So you can notice this D can bring E. This D, this can bring E. So this D can bring E. What else? Can anyone bring F? Can anyone bring F? Can anyone bring F? No. No one can bring F. Yes or no? Only F can bring F. So that's it. So this is your answer. Now let's move on. This is your GATE exam question. So let's solve it. This is GATE Computer Science 2006 question. The following functional dependencies are given to you. Which one of these options is false? Some options are given to you. The question is asking which option is false. The question is asking closure. Yes or no? The question is asking what is the closure of set of attributes. So tell me which option is false. Let's start. Let's do it one by one. So what is CF closure? What is a CF closure? See, remember, this is the symbol for closure. But I told you some people, some authors, they use star also, no problem. Okay, you can understand that this is closure. So tell me, what is CF closure? What they will bring? CF. See, CF will bring CF by reflexivity. CF can bring CF by reflexivity. Yes or no? Because of reflexivity, because of trivial functional dependency, CF brings CF. This is your reflexive law. Okay, this is your reflexivity. So you can start with CF. Now, what these CF can bring? These two people together, what they can bring? Remember, C itself can bring G. This C, this itself can bring G. So you got G also. You got G also. Now, these three people, what they can bring? These three people, what they can bring? See, this F can bring E. This F can bring E. So you got E also. Okay. Remember, this G can bring A. This G can bring A. So you got A also. You got A also. Yes or no? You got A. What else? Tell me. What else you can get? Let me know. Can you get something else? Can I get something else? Now, this is the family. Now, these five people, what they can bring? Can they bring B? Can they bring B? Can they bring B? No one can bring B. Only B can bring B. Yes or no? See, on the RHS, you don't have B. Notice. On the RHS, you don't have B. So can I say only B can bring B? Can I say only B can determine B? Agree with me? Because on the RHS, you don't have B. Only B can determine B. On the RHS, you can see on the RHS, there is no B. On the RHS, you don't have B. So only B can determine B. Very simple. What else? What else? Let me know. Tell me. What else we can determine? Can we determine something else? Please tell me. Is there anything else we can determine? Yes. This AF can determine D. Yes or no? This AF. See, these two people together. Look at these two people. These two people, AF, they can determine D also. So you got D also. What else? These two people, remember AF, they can bring D. Now you got D also. What else is remaining? A, B, C, D, E, F, G. Okay. A, B, C, D, E, F, G. Everything you got. B you cannot get. So that's it. See, B, only B can determine B. Only B can determine B. Everything else you got. So that's it. This is your answer. So tell me, this statement, the statement option A. Option A is true or false? Option A is actually true. The question is asking false. Okay. Now tell me, what about option B? What is the closure of BG? What is the closure of BG? What they can determine? See, BG can determine BG. Okay. BG can determine BG by reflexive property, by transitive, by trivial FD. This is your trivial FD that BG can determine BG. What else? See, G can determine B, G can determine A. This G can determine A. We can, okay, so you got A also. Now tell me, now remember this AB. AB can determine CD. AB, these two people, they can bring CD. They can bring CD. What else? Now you got this family. These 5 people, what they can bring? What they can bring? See, C can determine G. Okay, you already got G. What else you can bring? Can you bring something else? Tell me. Let's see. Can you bring something else? You cannot use this. C determining G, that is already over. You cannot use this. D determining F, but we don't have E. So that's it. Yes or no? Nothing else. That's it. So you cannot bring anything else. So that's it. So finally I can say, what about this statement? Is this true or false? This statement is actually true, but the question is asking false. Tell me the next one. What about option C? What is the closure of AF? What is AF closure? Tell me. AF can bring AF. AF can bring AF. What else? See, AF can bring D also. AF can bring D also. What else? What else? You got AFD. F can bring E also. F can bring E also. So you got AFDE. Now D can bring F. Okay, D can bring F, but that is already there. That is already there. What else? Can I use this? I cannot use this because I don't have AB. I cannot use this because I don't have G. F can determine E, that I already used. C can determine G, but I don't have C. Okay. So that's it, right? Yes or no? So you cannot do anything else. You cannot do anything else. So this statement is actually false. The question is asking false. So option C will be correct. What about option D? Please tell me. What about option D? What is the closure of AB? Let me know. The closure of AB, what that will be. See, you can see AB can bring ABCD. AB can bring ABCD. These 4 people you got. Okay, very simple. Now, what else? C can bring G. C can bring G. You got G also. Okay, now you have ABCDG. G can bring A, but A already have. We already have A. Okay, what else? Tell me what else? What else? Can we bring something else? See, I cannot use this because I don't have F. I cannot use this because I don't have E. I cannot use this because I don't have F. So that's it. Yes or no? Is this clear? See what I'm saying. Just notice. These 5 people I have. Now notice. I cannot use this because I don't have F. I don't have F, so I cannot use this. I don't have E, so I cannot use this. I don't have F, so I cannot use this. Yes or no? This I have already used. This I have already used. This I have already used. So that's it. So finally, what about this statement? This statement is actually true. So the question is asking what are false statement? The answer will be option C. Okay, so this is your GATE 2006 question. Understood? Please tell me. Are you confident? Finding the closure. That is very interesting, right? Very simple. Very simple. Let's move on now. So this is the closure finding algorithm. This is what we have seen. Basically, family is growing bigger. See, you can see this chart. Look at this. How to find closure? Computing the closure of set of attributes. So how to do that? First, you have initial set of attributes. Then you keep growing. Yes or no? Agree with me? You keep pushing out. Finally, you will get the closure. Do you agree? This is what we have done. Computing the closure of set of attributes. You have initial set of attributes. Then you keep growing the family. Okay, keep bringing more people. Is this clear? Finally, you will get your closure. Very simple. This is the idea. Now let's see the concept of keys. Can we define keys in terms of functional dependencies? How to define keys in terms of functional dependencies? So let's see this topic. This is a small topic. So let's understand this. Tell me the answer for this question. Tell me what the answer. In a relation R, A, B, C, D, when will this FD violate? Tell me. When can I say this FD will violate? You have a relation R, A, B, C, D. Then when can I say this FD will violate? This FD will violate if you can create this type of situation. Okay, remember, this FD will violate. I can say this FD, this is your FD A determining B. This FD violates if there exists an instance, I can say, if there exists an instance with the following situation. Okay, so if there exists an instance with the following situation, this type of situation you can create. You have A, you have B. Can you create this type of situation that you have same value for in two tuples, you have same value for A, but you have different value for B. You have different value for B. Okay, is this clear? Very simple. So remember, this FD will violate, this FD A determining B, this FD will violate if and only if there exists an instance, you can create this type of instance, you can create where you can see in two tuples, A value is same, but B value is different. Is this clear? Very simple. We already know this. And tell me, if you can never create this type of situation, then this FD will hold. Yes or no? If we cannot create this type of situation, then this FD will hold. Tell me the answer for this question. When this FD will violate, again, this FD will violate. Again, what I can say this FD, again, I can say this FD will violate if and only if there exists an instance. If and only if there exists an instance, you can create an instance. You can create, there exists an instance such that in two tuples AB is repeating. Okay, there are two tuples T1, T2, such that this AB, this combination is repeating. This combination is repeating XY, XY. This combination is repeating, but this combination is different. Okay, this combination is different. So this type of situation, if you can create this type of instance, then I can say this FD will violate. And if you cannot create this type of situation, you cannot create two tuples with the same AB values where CD values are different. If you cannot create this type of instance, then this FD will hold. Yes or no? Very simple. Tell me the answer for this question. Quickly tell me. In a relation R, if we already know that attribute A never repeats in two tuples of any instance, you already know this. In a relation R, if we know that this attribute A never repeats in two tuples of any instance, whatever instance you take, then what will be A closure? In this situation, can I say A will determine everything? Yes or no? In this situation, remember what we are saying. We are saying A value can never repeat. Just focus. We are saying A value can never repeat. You can never repeat. This A value will never repeat. This will never repeat. If this will never repeat, can you violate this FD? This violation is possible or not? Please tell me. This violation is possible or not? Please tell me. This violation not possible? Do you agree? Is this clear? Let me know. So very simple point. If you know this A value will never repeat, this will never repeat, then this violation is never possible. If this violation is not possible, what it means? So very simple. This is your relation A, B, C, D. And we are saying that this can never repeat. This can never repeat. In any instance. In any instance, whatever instance you take. Okay, in any instance, this can never repeat. If this can never repeat, then what I can say? Then you can notice these FDs will hold. Then this FD will also hold. This FD will also hold. This FD will also hold. Then A will determine everything, right? Yes or no? Can you notice A will determine everything? A will determine the entire relation. I can say A will determine the entire relation. The entire relation. Is this understood? Please tell me. You cannot violate this. If this A value will not repeat, if you do not repeat this A value, this can never repeat, then you cannot violate this. You cannot violate. You cannot violate. So all these functional dependencies will hold. So A can determine everyone. A can determine this. A can determine everyone. It can determine. So A can determine the entire relation. Okay, is this clear? Tell me. Tell me the answer for this question. If you know X is super key, if you already know X is super key, then what is X plus? If you already know X is super key, tell me, if X is super key, can it repeat? You know the definition of super key. Super key can never repeat, yes or no? Super key can never repeat. Super key never repeats in two tuples. You already know. Super key never repeats in two tuples. Correct? Super key can never repeat in two tuples. Is this clear? Yes or no? So you can see super key can never repeat. If this is a super key, if this X is a super key, then you already know that super key can never repeat. Super key will never repeat in two tuples. So again, the same thing. If this never repeats, then this will determine everything. Yes or no? Then X plus will be your entire relation. X plus will be your entire relation. Your entire relation. Or I can say that X can determine the entire, all the attributes. X will determine all the attributes. Yes or no? So remember, this is your set of all attributes. In this situation, this will be set of all attributes. Is this understood? Please tell me. Did you understand? Let me know. So this will be your set of all attributes. Very simple. Tell me the answer for this question. In a relation R, if X plus is entire R, means you can determine all the attributes. If X plus is entire R, you can determine all the attributes you can determine. Then what is X? If you can determine all the attributes, you can determine all the attributes. Then what is X? What is X? This information is given to you that X can determine all the attributes. Then what is X? The answer is a super key. This is wrong. This is wrong. This is wrong. See, this information is given to you that X can determine the entire R. Can I say this will be candidate key, X will be candidate key? No, candidate key must be minimal. Let me give you example. Let me give you this example. Consider this student table. Consider this student table, and let's assume you have SID, student ID, student name, and student marks. Okay. Now, let's assume that this is the candidate key, or let's assume this is the primary key. Let's assume this is your primary key. Let's assume this is your primary key. And let me also assume that here you have Aadhaar number. Okay, your Aadhaar number also. So your Aadhaar number is what? That is your candidate key. Yes or no? This is your candidate key. Agree? This is your candidate key. Now you tell me. Just tell me this point. Just tell me this point. If I take X equal to SID, S name, will it determine all the attributes? Tell me. X plus will be all the attributes or not? X plus will be all the attributes or not? Please tell me. X plus will be all the attributes. But can I say X is candidate key? Can I say X is candidate key? Notice. X is determining all the attributes. Notice X is determining all the attributes. But can I say X is candidate key? But can I say X is candidate key? No. This X is what? This X is super key but not candidate key. Look at this X. This is super key. This is super key but not candidate key. Did you understand this? Remember, candidate key is a super key which is not minimal. This extra condition is there in a candidate key. This extra condition is there. This candidate key is a super key which is minimal. Which is minimal. Don't forget this extra condition. There is an extra condition in a candidate key. Is this clear? This candidate key has an extra condition that this must be minimal. Understood or not? Please tell me. So you can see here, for example, let's assume this is X. X is SID, S name. This is your X. Now you can notice X can determine everything. Okay, this combination can determine everything. All the attributes you can determine. But you can see that this X is super key but not candidate key. Is this clear? So now tell me the answer again for this question. If X plus is entire R, can I say X is candidate key? If X plus is entire R, can I say this will be candidate key? No, but the answer will be super key. Understood? Did you understand that the answer will be super key? So remember, this is a very interesting point, and don't make mistake here. In any relation R, in any relation schema, you can also call it scheme. Either you can call it schema or you can call it scheme. Both are same. In any relation scheme R, X is super key if and only if. Tell me, X is a super key. When can I say X is super key? X is super key if and only if. If and only if X closer is equal to R. Is this clear? Please tell me. So remember, this is the definition of super key. This is not the definition of candidate key. Okay, this is the definition of super key. If this happens, then super key will be the answer. Okay, so remember this point. Is this clear? So remember this point, that if this happens, that X plus is equal to R. If this happens, then X will be super key. You cannot say that S will be candidate key, but you can say X will be super key. Okay. And if X is super key, then this will happen. Is this clear? For a candidate key, what do you need? Tell me. When can I say X will be candidate key? Tell me. You have a relation R. X is set of attributes. X is a set of attributes. Now you tell me, when can I say X is candidate key? Tell me. X is a candidate key. When can I say? X is candidate key means two things should happen. This and this. Two things should happen. That X must be super key first of all. And X is minimal. Yes or no? These two things should happen. This and this. Now you tell me, this X is super key. What this means? This is same as what? X is super key. What this means? Please tell me. X is super key. That is same as X plus will determine everything. Okay. And X is minimal. What this means? It means that if Y is subset of X, then Y is not a super key. Yes or no? Okay. Yes or no? What this means? This means if Y is a proper subset of X, then Y is not super key. Understand? Yes or no? This is the definition of minimal. X is minimal. It means if Y is proper subset of X, then Y should not be a super key. This is the idea of minimal. So tell me. So I can simply say X is minimal. What this means? That it means that if Y is a proper subset of X, then Y plus is not equal to R. This is the definition of candidate key. Okay, let me give you the conclusion. What is the definition of candidate key? Remember, this X is candidate key. When this will be candidate key? This will be candidate key if and only if two things should happen. Two things must happen. The first thing, X must determine everything. Okay. And the second thing, that is also important. What is that? The second thing is no proper subset of X. No proper subset of X can determine all attributes. Yes or no? Can determine all attributes. Please tell me, did you understand this? Did you understand the difference between candidate key and super key? What is the difference between candidate key and super key? Understood? So remember, X is a candidate key. When can I say X is candidate key? This is important. When can I say X is candidate key? X is candidate key means it must be a super key. It must be a super key. What that means? It must be a super key means X plus must be all the attributes. Okay, X must be super key. And if Y is a proper subset of X, then tell me what I can say about the closure of Y. Closure of Y should not be same as R. Yes or no? Y cannot determine all the attributes. Is this clear? This is the entire definition of candidate key. This is the definition of candidate key. Please tell me, understood? Did you understand this? Let me know. Because remember, candidate key means, what candidate key means? This means it is a super key. This means super key. And this means minimal super key. Okay. So very simple. Remember, this means a super key. What this means? This means a super key. This means super key. And tell me what this means. What this remaining thing means. This remaining thing, what this means? This means minimal super key. Yes or no? This is minimal super key. Understood? Please tell me. So it is a super key which is minimal. It is a super key which is minimal. So this is the idea. So this is minimal. Okay. So quite easily you can do this. Understood? And what about primary key? What about primary key? Tell me. When can I say X is primary key? When can I say X is primary key? Please tell me. Can you determine if X is primary key? Can you determine if X is primary key? Primary key we cannot determine. Remember, primary key we can never determine. This is given. Please understand that primary key cannot be determined. This is always given in the question. Is this clear? Because if you have many candidate keys, one of them is chosen as primary key. And to choose, is there any specific rule? Tell me. If you want to choose, is there any specific rule? No. You can choose any of them which is not null. Is this clear? So remember this point. Let's assume in your relation, you have 5 candidate keys, out of which 3 are not null. In your relation, you have 5 candidate keys you have, out of which 3 are not null. Then tell me, any of them can I choose as a primary key? Any one of these 3 can I choose as primary key? Yes. So for primary key, there is not a specific rule. Agree with me? So remember, you cannot determine primary key. Primary key we cannot determine. We cannot find out primary key. We can find out super key. We can find out candidate key. But we cannot find out primary key because one of the candidate key is chosen as primary key. Okay. One of the candidate key we choose as primary key. And that is your choice what you want to choose. There is no specific rule. So remember, primary key cannot be found. This is given. Is this clear? Is this clear? Remember, primary key is not found, cannot be found, but it is given. Primary key is always given. Always given. We cannot find. Okay, we cannot find. Is this clear? Please tell me. So this will always be given to you. You cannot find it. Okay, so they will give you in the question. So don't worry about the primary key. They will give you in the question. Did you understand super key and candidate key? Did you understand that? Tell me, what the definition of super key and what the definition of candidate key? So what the definition of super key? What the definition of super key? Super key X. What that means? That means X plus determines all the attributes. Yes or no? X can determine all the attributes. This is the definition of super key X. And what the definition of candidate key? When can I say X is candidate key? Candidate key X. When can I say X is candidate key? This must be minimal also. So remember, X plus must determine all the attributes and this must be minimal also. And X is minimal. And X is minimal. Okay, so very simple. So this is the idea. Now let's move on. So remember, what is a super key? Super key is basically if you can functionally determine all the attributes. Okay, K is a super key. K is super key if you can functionally determine all the attributes. Okay, and candidate key. Remember, key means what? If I only give you key, this word key is given to you. What this means? Super key or candidate key? This word, what it means? By default, this word candidate, this means candidate key. I told you. Okay, this word by default, it means candidate key. It does not mean super key. It does not mean primary key. This word by default, it means candidate key. Okay, this I told you. Okay, I also gave you some source. Source was Ullman. Yes or no? So anyway, this is the idea. Okay, so remember, whenever someone uses this word key, then this is always candidate key. Okay, take it always candidate key. But remember, in the GATE exam, you will not have any difficulty. In the GATE exam, they never mention it. They will always give you candidate key. In the GATE exam, they always mention super key, candidate key, primary key. They will never use this word key. Is this clear? But if they use, I'm telling you, if they use, then this is candidate key. Is this clear? In the GATE exam, if they use this word key, then it means candidate key. Okay, now let's move on. So you can see K is a key. When can I say K is a key? K is a key if it is a super key and it is minimal. It is a super key and it is minimal. Means no proper subset is a super key. So this is the definition of candidate key. Okay, so we have seen everything. Just let's take this example. Consider this example. This relation is given to you A, B, C, D, and these functional dependencies are given to you. A is not candidate key. Why? Tell me. A is not candidate key. Why? See, this relation is given to you. These functional dependencies are given to you. A is not candidate key. Why? Because notice A is not even super key. Okay, what A can determine? What A can bring? A can determine A can determine B, A can determine C, but you cannot determine D. D is missing, but D is missing. So this A is not even a super key. Can I say this A, this is not even a super key? Agree? I can say this A is not even a super key. Forget about candidate key. This is not even a super key. Okay, what about this? What about this ABD? Tell me, what about this ABD? See, A is not a super key, so it is not a candidate key also. A is not a super key. You cannot bring this D. Don't forget this D. Don't forget this attribute. This attribute. Don't forget this attribute. So remember, A cannot determine all the attributes. The closure of A is ABC. The closure of A is not R. That is not same as R. So I can say this A is not even a super key. If it is not a super key, so it is not a candidate key also. What about ABD? What about ABD? Tell me. What about ABD? See, if you look at ABD, what it can bring? Can it determine everything? Can it determine everything? Yes, ABD can determine ABD. And you can notice B can determine C. So that is equal to R. That is equal to R. You got R. So this is a super key. This is the definition of super key. Okay, from here, what I can conclude? From here, what I can conclude? I can conclude that ABD is a super key. I can conclude ABD is a super key. I cannot say it is a candidate key. I cannot say it is a candidate key. Because what is the reason? Because this is not minimal. Actually, AD is candidate key. You can see AD can bring everything. AD can bring everything. AD can bring AD. A can bring B. B can bring C. Okay, so AD is a super key. And can you notice? Can you notice? Can you notice that A cannot bring anything? A cannot bring R. D cannot bring R. So please understand. Look at this. Look at this AD. This AD can bring everything. So this AD is a super key. So this AD is a super key. Is this clear? What is this AD? This AD is a super key. This is a super key. Is this clear? But remember, why can I say that this is a candidate key? Now, how to check if AD is candidate key? Check AD is a candidate key or not. Then what you will do? Then what you will do? Check AD is a candidate key or not. What you will do? Now you will check, can A determine everything? Can A determine everything? No. Can D determine everything? No. Okay, yes or no? So you can see A cannot determine everything. D cannot determine everything. Now I can say that. So now we can say that AD is candidate key because AD is minimal. Is this clear? Now we can say AD is candidate key because it is minimal. Is this clear to everyone? Please understand that I am saying that AD can determine everything. If you look at AD can bring everything. AD can determine all the attributes. But Now you have to check, is it minimal? You have to check, can a proper subset of it determine R? Can a proper subset of it, is this minimal? So now you will check the proper subset. You will check, can A determine R? No. Can D determine R? No. So now you can say it is minimal also. So finally I can say AD is a candidate key. So this is the idea. Understood? Please tell me. So this is the concept of candidate key and super key. I hope you understood everything we have seen. Is everything clear so far? So far, everything that we have seen, every concept, did you understand? Please tell me. Every concept, whatever we have studied in this lecture, please tell me, did you understand? Okay. So thank you, everyone.